Here is a region bounded by the graph of that equation and these two lines. Now let's see if you and I can't compute the volume of the solid of revolution generated by revolving this region about the line y equals -1. Well, revolving in that direction, or about that line, certainly my rectangles will be vertical. Whose thicknesses are in the x direction, which clearly identifies my variable integration as being x. Putting in the other details. Now, the outer radius is nothing more than this large y value minus small y. But that large y value is 10. The small y value is -1. And so here's the outer radius. As I just said, the large y value minus the small y value. But the radius is squared. Now, as far as the inner radius is concerned, that will be described as this vertical length. But again, here too, it's just this y value minus that one. And so I think it's going to be a y minus -1. But the y described in terms of x is as such, minus my -1. That's the inner radius, so I'll square it. I will integrate all of that with respect to x. And my bounds are simply going to be one extreme x value to another extreme x value. Whereas this point of intersection is located here. This point of intersection is located at a y value of 10, whose x value will be the natural log of 10. Looks to me like my bounds integration are from here to here. Now, if I'm not being too sloppy, let's see if we can't evaluate. I'm just checking to see if we can still see this on the board. sorry, maybe that was a bit of a waste of our time by me actually finishing the numerical evaluation. I should certainly be focusing on the setup of these definite intervals that allow me to compute the volume of a solid of revolution using this new washer technique.